This presentation deals with the LCA methodology for nanoproducts in the construction sector. It has been created by NanOER project, Erasmus consortium. Specifically, the Technology Center of Marble has worked on this content. The contents of the presentation are the following. 1. Initially, we will make a brief introduction to why it is necessary to apply the LCA methodology to the construction sector. 2. Then, we will define the basic concepts in order to fully understand the flashcard. 3. We will proceed to scope the current situation of the use of LCA calculations associated with nanoparticle-based products. 4. Afterwards, we will show an example calculation to facilitate the understanding of the methodology. 5. Finally, the conclusions obtained will be presented. The construction industry, along with the material industries that support it, is a major consumer of natural resources and significantly contributes to global unsustainable development. Construction activities have notable environmental impacts, including emissions, noise, waste generation, water use, and air pollution. This sector accounts for approximately 40% of carbon emissions, up to 50% of natural resource consumption, and half of total solid waste. Additionally, challenges such as a non-circular economy, limited financial support, outdated technologies, inadequate infrastructure, and lack of political commitment hinder progress towards sustainable development. Buildings are omnipresent in modern society and have a significant environmental impact throughout their lifespan, from resource consumption during construction to land occupation and eventual demolition. With the growing interest in sustainability, particularly in the construction industry, more attention is being directed toward eco-friendly materials and innovative technologies. However, products that seem cost-effective at first may lead to higher long-term maintenance or waste management costs. This highlights the importance of life cycle thinking, which guides decision-making to select the most sustainable options and minimize environmental impact through thoughtful design and renovation practices. Life cycle refers to the series of stages a product undergoes, starting from the extraction and processing of raw materials, through production, transport, marketing, use, and maintenance, to its final disposal at the end of its useful life. The environmental impact of a product is determined by the total inputs of materials and energy required, as well as the outputs in the form of waste and emissions generated during these stages. Life cycle assessment, LCA, is a widely used method to assess environmental burdens of a product, service or process throughout their entire life cycle, from the extraction of raw materials to their disposal, from cradle to grave, in order to assist consumers in making decisions that will benefit the environment. The main goals of LCA are to quantify or otherwise characterize all the inputs and outputs over a product's life cycle, specify the potential environmental impacts of these material flows, and consider alternative approaches that change those impacts for the better. The objectives of life cycle assessment, LCA, are as follows. Provide comprehensive environmental information, to offer complete, objective, and transparent data on the interactions of a product, process, or activity with the environment across all stages of its life cycle, enabling informed decision-making. Understand environmental interdependencies, to enhance the understanding of all interconnected environmental consequences arising from human activities, highlighting the broader impacts and trade-offs of these actions. Anticipate and mitigate negative impacts, to foresee potential negative environmental consequences of decisions and identify opportunities for improvement, promoting sustainable practices and reducing harm. Foster societal dialogue, to facilitate constructive communication and collaboration between various sectors of society, industry, policymakers, researchers, and the public, focused on environmental quality and sustainability. The Life Cycle Assessment, LCA, consists of the following key stages, each playing a crucial role in evaluating and minimizing environmental impacts. 1. Goal and scope. 2. Life Cycle Inventory, LCI. 3. Impact Assessment, LCIA. 4. Interpretation. These stages are iterative and interconnected, allowing refinement and validation of results throughout the process to ensure accuracy and reliability. We will now look at each of the stages in more detail. Definition of objectives and scope defines the objective and intended use of the study, as well as the scope according to the system boundaries, the functional unit and flows within the life cycle, the required data quality, and the technological and evaluation parameters. Development of the Life Cycle Inventory, LCI. This is the phase of the LCA in which data is collected on the inputs and outputs for all processes of the product system. Life Cycle Impact Assessment, LCIA, is the phase of the LCA in which the inventory of inputs and outputs is transferred to indicators of potential environmental impacts to the environment, human health and natural resource availability. Interpretation. This is the phase of the LCA in which the results of the LCI and LCA are interpreted according to the objective and scope initially set. In this phase, an analysis of the results is carried out and conclusions are drawn. We now turn to the nanotechnology part. In order to be able to assimilate the LCA calculation of nanoparticle-based products, it is necessary to understand the following concepts. Nanoparticle. A nanoparticle or ultrafine particle is a particle of matter ranging from 1 to 100 nanometers, nm, in diameter. Nanomaterials, NMs, are chemical substances or materials with particle sizes between 1 to 100 nanometers in at least one dimension. Due to an increased specific surface area by volume, nanomaterials may have different characteristics compared to the same material without nanoscale features. As a result, the physicochemical properties of nanomaterials may differ from those of bulk substances or particles of a larger size. Nanoproduct is any product containing nanoparticles. A variety of NMs can have beneficial applications in construction that encompass superior structural properties, functional paints and coatings, and high-resolution sensing/actuating devices. The nanomaterials used in the construction sector are called manufactured nanomaterials, which are those that have undergone manufacturing processes. Following, nanoparticles containing materials used in the construction industry have been identified, defining its properties and applications in the sector. Here we can look at the main applications of the most frequently used nanoparticulate products in the construction sector and the benefits they bring to them. Life cycle assessment operates within a well-defined legal framework, established primarily by the N-ISO 14040-2006 and N-ISO 14044-2006 standards. These documents provide the principles, framework, and detailed requirements for conducting an LCA. Key elements include the definition of life cycle phases, from goal setting to impact assessment and interpretation, and the need for transparency in all processes, including the selection of system boundaries and functional units. The primary goal of these standards is to ensure methodological consistency and scientific rigor, allowing for credible and comparable assessments. In the context of nanomaterials, these standards are flexible enough to accommodate the evaluation of nanospecific impacts, such as toxicity and environmental fate, ensuring compliance with global best practices. The scope of the Life Cycle Assessment, LCA, for nanomaterials focuses on their entire life cycle, from production to utilization and disposal. This approach allows for a comprehensive evaluation of environmental and human health impacts. Key frameworks, such as those provided by the REACH Nano Consortium and the CEN/TS 17276/2018 standard, offer robust methodologies for incorporating LCA into the assessment of nanomaterials. These guidelines emphasize the importance of evaluating the unique properties of nanomaterials, including particle size, reactivity, and potential toxicity, to ensure accurate and meaningful results. To enhance the effectiveness of LCA studies for nanomaterials, certain recommendations should be considered. First, the focus should be placed on nanoproducts rather than isolated nanoparticles, as emissions and releases predominantly occur during the use and end-of-life phases. Second, adopting a cradle-to-grave perspective ensures that environmental and toxicological impacts are captured across all life cycle stages. For phases where data is limited, scenario-based sensitivity analyses are advised to address uncertainties. These measures are critical for supporting sustainable practices in the construction sector. The Life Cycle Inventory, or LCI, represents the first operational phase of LCA. This stage involves compiling and quantifying the inputs and outputs of materials and energy throughout the life cycle of a nanomaterial. The analysis is divided into three key phases: production, use, and end of life. Inputs include energy, raw materials, and water, while outputs encompass emissions, waste, and products. For nanomaterials, specific considerations such as size, shape, and physicochemical transformations must be integrated to ensure precise evaluations. The Life Cycle Impact Assessment, LCA, is the phase where inventory data is translated into indicators of potential environmental impacts. This step focuses on evaluating categories such as human toxicity and ecotoxicity, which are particularly relevant to nanomaterials due to their unique properties, including surface area and reactivity. LCA provides actionable insights by identifying and quantifying the material flows that contribute most significantly to environmental burdens, facilitating informed decision-making. Interpretation is the phase where the results of the inventory and impact assessment are analyzed to draw conclusions and provide actionable recommendations. This process involves identifying key contributors to environmental impacts, highlighting uncertainties and limitations, and ensuring alignment with the study's defined objectives. Reporting serves as the final stage, where findings are documented in a clear and comprehensive manner to ensure transparency, reproducibility, and utility for stakeholders. This step is critical for guiding improvements in the environmental performance of nanomaterials throughout their life cycle. The findings highlight the significant role of life cycle assessment in fostering sustainable practices within the construction industry. Nanomaterials, while offering distinct advantages such as enhanced durability and self-cleaning properties, require meticulous life cycle analysis to address their environmental and toxicological impacts. To advance sustainability, it is essential to invest in research to fill existing data gaps, particularly concerning toxicity and long-term environmental effects. Furthermore, promoting the adoption of eco-friendly nanotechnologies can contribute to reducing energy consumption and resource use in the construction sector. These measures are integral to achieving a more sustainable future for the industry. Here you may find the main review articles with the information presented.